This is section 13.5, and this is examples 2 and 3 in our notes. Example 2 is actually the exact same equation, or the same vector that we used in example 1, but we're just going to rephrase a question about it, and it's connected to that little theorem we just talked about in the notes at the bottom of that second page. If we have, in this case, the curl of vector f equal to negative 2y minus y squared and x and yz, this is not equal to 0. And so if we want to show that this particular vector is not conservative, we can just calculate the curl of the vector, and if that curl that curl vector is not 0, then that particular vector is not conservative. So again, that was just that little theorem that we were talking about in the previous video. Okay, so let's use that theorem here in example 3. Okay, so then the first thing we're going to do is we're going to calculate the curl of f. And the reason we're going to do this is that we're going to show this particular vector field is conservative. And so therefore what we're looking for is to get 0 here. Let's go ahead and set this up. I'm going to pause and then set this all up. Okay, so finding the curl of f, we have our determinant here, and we perform our partial derivative operations, and what you can see is that we end up getting 0 for each of our 3 components here. And so since the curl of f is the 0 vector, then this is a conservative vector field. So then our next step is that since it is conservative, we're going to find a potential function that satisfies this particular vector field. So remember, what we're looking for is a function of x, y, and z such that the partial derivative of f with respect to x is equal to the first component. The partial derivative with respect to f of y is the second component. And the partial derivative of f with respect to z is the third component. So that's what we're looking for here. And again, our strategy is that we'll just start with the first one. And when we look at this first one, the antiderivative of this with respect to x would simply be x, y squared, z cubed. Now let's check this. If we were to take the derivative of this with respect to y, we would get 2x, y, z cubed. So this particular function satisfies the second partial derivative. Let's check again with respect to z. So if we take the derivative with respect to z, we get 3xy squared z to the second, and it satisfies the third one as well. So this is actually good enough for all 3 partial derivatives. We just have to add a plus c, and we're all set. Okay, on the next video, we will introduce the idea of divergence and then do our next set of examples.